So yesterday I made a small error, and the error was I wrote some wrong basis state. So the first basis state was 1 2 and 3 1, and the second basis state was 3 1 and 1 2. Okay, so this was the mistake. Please incorporate it in your. Now to compensate what the mistake that I did, I'll do a complete calculation related to this example so that no confusion remains further. Okay, so please note this mistake down, and let's start today's class. So yesterday I told you that if you have a transformation of basis such that you go to the new basis by using a certain matrix that makes the transformation. Okay, so you go from old matrix to new. So let's write it like this. So you go from old matrix to new, then the transpose of this matrix. So let me write A transpose Ji. Okay, so the transpose of the matrix relates the new coordinate with the old coordinate. So here we are going from new to old, and as I said that A tilde Ji is actually the transpose of Aij. So if I just reverse the indices, that would do. Okay, so the tilde here is the transpose of it. Anyways, so let me not write it in this way. So in a more easy way, let me do it in this way. So a shortcut. So if I have u prime equals a u, then x equals a transpose x prime. Okay, so this is what you need to remember, and I will not only give an example, but I will prove it to you. So yesterday I just claimed this thing, but now I will prove it, and after the proof I will give an example, and the example will contain the same example we did yesterday with modification of the errors. Okay, so the first work is I need to prove it. So proof. Now for simplicity, I'll do the proof in 2D. Okay, so how should I do the proof is the following. So consider, let's use a different color, and this one looks good. So now consider that u I prime is equals a ij uj. What does this mean? It means that in 2D you have two new bases, say u1 prime, u2 prime equals, and then it will be a 2 cross 2 matrix. It's quite clear because we are in 2D. So a1 a11 a12 a21 and a22, and this will get multiplied with the old basis, so u1 u2. So this is how I made a transformation of basis. Okay, now again, to give you an example of this matrix, let me give an example. So I will do the proof along with examples. Okay, that would be better. So as an example, remember that consider you have one basis B, which is 1 2 comma 3 1. So say this is one basis, and the new basis C equals 3 1 and 1 2. Okay, so how is this written? this is written like this. So the new basis is equals to some matrix acting on the old basis. Okay, so let this be my u1, u2, and let this be my u1 prime, u2 prime. So C is my new basis. Okay, so if C is my new basis, then how should I write the transformation? I should write it in this way here that I have written. And now we need to calculate what the matrix A is. So how we do the calculation? So if I write this matrix in a simple way, then you can see that u1 prime equals a11 u1 plus a12 u2, and u2 prime is equals a21 u1 plus a22 u2. Okay, now what we need to find the coefficients of the transformation matrix. That is, we need to find a11, a12, a21, a22. How to do? So what is u1 prime? u1 prime is 3 1. So it's 3 1. Okay, now what is my u1? u1 is 1 2. And what is my u2? u2 is 3 1. So now I'm gonna find the coefficient such that if I do the calculation, I should get 3 1. So obviously the coefficient here should be 0, and here the coefficient should be 1. It's quite clear. What is u2 prime? u2 prime is 1 2 equals, what is u1? u1 is 1 2, and what is u2 is 3 1. So I get a 0 here and a 1 here. It was a very easy example. Now, so what is my transformation matrix A? My transformation matrix A is 0 1 1 0. Okay, so now I gave you an example how to calculate this. Now what is the next step? The next step is my claim that A transpose is the matrix that will help you to go from one coordinate to another coordinate, but the reverse. You go from the new to the old. So the next part of the proof is that consider you have a matrix X. You have a vector X. Okay. Now this vector X has two coordinates, say x1 and x2. As you can see, these coordinates are in the old basis. So I can expand X as x1 u1 plus x2 u2. Remember that the vector X, the coordinates of a vector X depends on where how you are writing and in what how you are writing in terms of basis. So here the basis is u1 and u2, hence the coordinate is x1 and x2. The same matrix X, if written in another basis, then it will have a different coordinate. That implies that my same vector X can be written as x1 prime u1 plus x2 prime u2 prime. Sorry. So this is the new coordinate. Okay, quite clear. Now what I can see from here, I can see a very interesting thing. I start with X vector, then I write it in terms of, oh, let's do it in the new page. That would be better. So what I'll do is I'll start with X prime equals, what do I get? x1 prime u1 prime plus x2 prime u2 prime. But we know how u1 and u2 is related to the old basis through the matrix. So let me remind you that u1 prime was a11 u1 plus a12 u2, and u2 prime was A21 U1 plus A22 U2. Now substitute it. Oh, I should not have written here prime. That's bad, because the vector does not change. It doesn't matter whether you write it in one basis or the other base. It doesn't matter. The vector is a vector. It doesn't change. So now x vector is equals to x1 prime. So in U1 you write A11 U1 plus A12 U2 plus x2 prime A21 U1 plus A22 U2. Now vector plus plus x2 prime A21. And what is the basis? The basis is U1 plus
I
x1
cannot
prime.
see your screen anymore. Oh, it came back.
Okay, were you able to hear me? So what I was doing is I wrote this one, and now I'm writing the entire thing by taking U1 common. So first I took U1 common, now I'm going to take U2 common. So I get x1 prime A12 plus x2 prime A22 and U2. That's very beautiful, because now I can compare this with x1 U1 plus x2 U2, right? Now when you compare it, so you compare this, so you compare this and you compare this. So when you compare, you get a very interesting result. It turns out that x1 is equals to x1 prime A11 plus x2 prime A21, and x2 turns out to be x1 prime A12 plus x2 prime A22, right? Now A11, A22, these are what? These are just numbers. So it doesn't matter, I can write them in this way. x1 is equals to A11 x1 prime, because it's a number, A21 is a number, so I just bring it to the left side. Similarly, I do this, I bring these numbers to the left and A22 to the left. Now look at this beautiful thing. So x1, x2, and you get what? A11, A21, A12, A22 of x2 prime, x1 prime and x2 prime. If you look at the matrix, this is nothing but A transpose. Let me remind you that A was used to change the old coordinates to new. And what was A? A was A11, A12, A21, A22. So this was my A, and you can see that the matrix that transforms the coordinate is a transpose of the matrix that transforms the basis. I think the proof is very easy and it was very clear. Any doubt? If not, as I said, to compensate the error, I'm going to use the entire analysis done here and I'll put it in an example. Should I continue?
Yes.
Okay. So as an example, so consider you had basis B as 1, 2 and 3, 1. And then consider you have basis C just 1 minute. And you have basis C, which is 3, 1 and 1, 2. And I already found the matrix A that was taking you from the old basis to the new. That is, C can be written as A, B. So this is what we did. And what was the matrix? The matrix turns out to be 0, 1, 1, 0. Okay. Now what we do? Now let me tell you what we already know. We already know that the vector, so you had a vector. What vector you had? You took a vector V equals 1, 7 in standard basis. So this is a vector. Now when you wrote this vector in terms of B basis, it turns out that coordinate of vector V when written in basis B was 4, minus 1. Our aim is to find what is the vector V when written in terms of in basis C. What are the coordinates here? But we already know the answer. The answer was, it turns out the coordinates are minus 1 and 4. So we found the answer in a different way. And now we find the answer in a different way. Okay. So what's the plan? The plan is, you will say that the A transpose of the matrix will help me find the new coordinate if I know the old coordinate. So according to the formula, where should I put the old coordinate? I should put the old coordinate here, and I should put the transpose of the A matrix here, and I should put the new coordinates here. Okay, clear? So let's do it in the next page. Okay, so as you can see that you already know this. So the B basis, you already know it is 4, minus 1. But you don't know what is the vector V in the C basis. But I said, if you know that matrix that transform the basis, its transpose will help you to find out VAC. But you need to write it in a certain way. You need to write the old coordinates here and the new coordinates here. Now what was A? A, as you remember, it was 0, 1, 1, 0. What is A transpose? I think you'll get the same matrix, 0, 1, 1, 0. It was a trivial example. So VB is equals to 0, 1, 1, 0 VC. But you need to find VC, right? So what you will do? VC, that is the coordinates in C, turns out to be the inverse of the matrix multiplied with VB. Okay, it turns out that if I'm correct, and please correct me, what is going to be the inverse of this matrix? Can you please calculate within 30 seconds? Please check out if you get the inverse of the matrix as the same matrix, 0, 1, 1, 0. Just check as I'm writing here. Please check it so that I don't make an error. Now what was VC? VC was V1 prime, V2 prime, 0, 1, 1, 0. And what was V? We already know V, right? So let me not write it in terms of V1 and V2. But let me just write the answer. It was 4 and minus 1. So what do you get? V1 prime, V2 prime turns out to be minus 1 and 2. You see, we got the answer. So that's the beauty of the formalism that we just found out. So if you know the matrix that transforms the basis, then you can automatically find the coordinate transformation using the transpose of the matrix. Okay, this is easy. Now, as Bikram asked yesterday, that what about going from, if you change your basis from different vector spaces? So consider you have a particular map that takes your basis from R3 to R2. Then I'm going to prove it to you now that the matrix that transforms the basis can be calculated, and the matrix that transforms the coordinates can also be calculated. And as I said, the matrix will not be a square matrix as we found above, but it's going to be a rectangular matrix. So let F, a map which takes you from R3 to R2, let this be a projection map. What is a projection map? So if you have F acting on any vector in R3, let that vector be x1, x2 and x3, then you are only going to get a vector in R2 as x1 and x2. So x3 goes out. Okay, so this is the definition of my map. Now using this map, I'm going to calculate what is the matrix that transforms the basis. Okay, so let us choose standard basis. And do our work. Now the map is here. It is written what the map is going to be. The map is going to be like this. Okay, the map is going to be. Yes. I already defined the map here. So if you have any element 1, 2, 3 in R3, then when you map it, you get 1, 2. I already told you how the map is gonna act. Okay. Okay. Bye. Yes. If I make projection like that, the projection is x1, x3, depends on me. But x1 and x3 is not a good projection because it may have a good geometrical meaning. So when you project x1 to x3 to x1 and x2, it means what? Projecting in which plane? So consider this is x, y, z, and if you are projecting only the first two x and y, that means you are projecting on xy plane. So projection operator here geometrically takes every point on the top of R3 and brings them down on the xy plane. Okay, so that's the geometrical meaning of this map. So let's remove it. No, which trace? Since I have not defined the matrix. For example, the example. Yeah, if you look at the trace, I think the trace is maintained. Yeah, because when you do the transpose of the matrix, the trace doesn't change. Okay, but it is a square matrix. That's why you are able to talk about trace. but how about rectangular matrices that we are going to encounter now? We'll look at it. We'll look at it. Okay. Oh, so let's use standard basis, and what we do is the standard basis in three are, we already know, it's 1 0 0 1 0 and 0 0 1. Let's start with the standard basis 1 0 0 in R3. Add the matrix, and what the matrix gives you, it gives you 1 0. Now you want to write this thing in terms of the basis in R2. You want to expand it. So if you want to expand it in the basis in R2, then you should have the other basis and you have to write the coefficients. Here the coefficient will be 1, here the coefficient will be 0. Similarly, when f will act on 0 1 0, then according to the projection you will get 0 1. That's the answer, but we want to expand it in terms of the basis in R2. So just for that I can write a 1 here and a 0 here. Now the third one is 0 0 1. The answer is 0 0. Now since the answer is 0 0, that means it is 0 1 0 and 0 0 1. So what is the matrix that transforms the basis? It is 1 0 0 1 and 0 0. That means the matrix that will help us transform the coordinates from R3 to R2 is going to be 1 0 0 0 1 0. I just take the I just take the transpose of the matrix that transforms the basis. So this helps you with the basis, and this helps you with the coordinates. Okay, so how you do it? Now what f does? So again, let me emphasize on the map. See why I'm teaching you in terms of map, because when we will do differential geometry, everything will have this kind of mathematics. So at each and every lecture I'm trying to tell you these mathematics in a very different, simple way. But anyways, so this map, what it does, so consider you have x belongs to R3, and consider you have a small x, oh sorry, this is R2, small x belongs to R2. That means when your map acts on the capital X, then whatever result you will get, which is small x, it will belong to R2. So some people will write this, that f of x belongs to R2 directly. This can also be written. Okay, so the matrix F transpose that we got, which is 1 0 0 and 0 1 0. Okay, this matrix actually helps you if there is any vector x belongs to R3 and you want to find what is x belongs to R2. So this one is gonna help. So let's do an example. How about we take an example? So when we write F transpose, so F transpose took you from this side we had R2 basis and this side we have R3 basis, and that's how you wrote. So this was old, this is new. So F transpose in terms of coordinates will take you, this side I should have new and this side I should have old. That means x is equals to F transpose capital X. I mean in terms of coordinates, right? In terms of coordinates. So better I write like this. So x1, x2, is F transpose X1 capital X2 capital X3. Okay, so why don't I just do it X prime capital, so that would be better. Okay, that will be better, so that I can put prime here, here, and here. Okay, this is good. Now I don't know if the example will work, so
Excuse
consider
me. We have one vector belongs to one space and another vector belongs to another space.
Yes, the capital X
And
prime
yeah,
belongs to
but in which space we define the transformation matrix?
the transformation matrix. I don't think it is defined in any space. It is just a transformation matrix, and the matrix that is defined using a space, that is a different question, which we will come to in the next part of the lecture.
Okay.
Okay, so don't I don't want you to think this matrix as defined in some space. You think of this matrix as a unique matrix that does the transformation.
Okay.
But the question that you have asked, I want you to also tell me whether the answer that I gave you is correct or wrong after you do the studies. Okay, so so we saw how F acts on the basis. So I'm not sure if I'm doing this all correct. Let us take a vector 1, 2, 3. So 1, 2, 3, and let us act the transpose that we find 1, 0, 0. Can we do this, Bikram? If I do this, what's the answer? It's gonna be 1. It's gonna be 2, and I think this is correct. Please check if I have done everything correctly. If you tell yes, I'll not explain, because anyways we understood that the matrix is a projection. So the projection matrix should always take a vector from R3, and it will give you a vector in R2 by only projecting the first one and the second one element, the first element and the second element. And you see the matrix F that transpose the basis, the matrix F that transforms the basis, the transpose of that matrix F helps us to get coordinate transformations through projection. So this is F transpose is a matrix representation of the operator that projects a vector in R3 to a vector in R2. Any doubt? So what do we get? We don't get a square matrix when you work with different spaces. You get a rectangular matrix. Now what you can do as an exercise, you can prove that it is a rectangular matrix by doing this. Remember when you did U1 prime is equals to A Ij Uj. When you did this, now imagine the I goes from 1 to 3 and the j goes from 1 to 2. In this way, you can find U1 prime is equals to A1 1 U1 plus A1 2 U2. U2 prime is equals to A21 U1 plus A22 U2. U3 prime is equals to A31 U1 plus A3 to U2. So as you can see, if I write it in short notation, U is equals to AU, then the matrix A that transforms the basis is no more a rectangular matrix, but it is now no more a square matrix, but it is a rectangular matrix. Now once you get the matrix that transforms the basis, then the transpose of the matrix will transform the coordinates. You can do the same derivation we did before, and you can reach the conclusion that A transpose will help you change the coordinates. Can you repeat this derivation yourself? Maybe take it as an exercise. So let me give you a hint how to do. You do this, and then you write the coordinate. Then you take a vector x, and you write it in terms of the basis, in new basis and old basis, and give it a try. Okay, try it yourself. If you want, I can give a generalized example which I think will be very interesting and a bit mathematically rigorous, so that I want you to introduce yourself to some rigorous mathematics. So let's do one thing. Let's end the class here. I want you to read this and come back again.